Hey guys, hope you're enjoying your weekend. I just wanted to hop on and um, just kind of give a little bit of an intro to our last two topics of Unit 4. That way we can kind of use class time more efficiently on just practice problems and have more time for our lab. So, first off, I did want to re-clarify. I think I might have misspoken in class when we were talking about net ionic equations. So I wanted to re-clarify. When I said breaking up anything soluble, that only applies to ionic compounds. I forget if I made that distinction in class, and I think I didn't. So just want to be really clear. Only ionic things break up in solutions. So like you don't have to draw this if you don't want to, but we've talked about it lots of times of like, if you have a salt and it's a solid like that, it has a lattice, and then once you put it in the water, it breaks up into the ions. Right? We've talked about that. But that is not the case for covalent things. So like here, like you've all like stirred sugar into like tea or something before, right? Like it looks like it goes away, it dissolves. Or anything that is miscible with water, any polar molecule is going to do this, but it's not breaking any covalent bonds. The structure of the thing is still there. Like, it's why your tea tastes sweet, like when you put sugar in it, it's still the sugar molecule. So yeah, just to clarify that. So only break up soluble ionic compounds. And then I guess the other thing that breaks up completely, that we just learned about, are strong acids. Okay, so those are the only things that dissociate, the only things that break up into their ions, is strong acids and bases we talked about, and then soluble ionics. Any other covalent thing, keep it as a unit. But if they're asking you to do a net ionic, it's like 90% of the time it's about a precipitation reaction. That's all ionic stuff. Okay, but just wanted to clarify that. Okie dokie. I'm gonna scroll down to 4.9, redox. So fun. So hopefully this is something we're a little bit familiar with. I'm just gonna, brief us on some of the vocab for this and just the skill of like oxidation numbers, and then we'll learn about half reactions in class together. So let's take a look at this. Redox. So this is a type of reaction where electrons are transferred I know, like, the first time you hear that, you're like, but aren't all bonds electrons being transferred? Yeah, but like redox specifically, we're talking about like the way we define it is the oxidation state of an element, like how many electrons like belong to that element at any given time. So even if it's forming like a new type of bond, maybe it's interacting with a new element, its electrons might have changed a little bit, but like has it actually transferred electrons? Does it actually have a different like, it's not a charge, but like something, it's kind of similar the way we write it. It's a little weird, but just know it's its own little category, and I'll teach you how to recognize it. So redox just means oxidation and reduction. So those are the two categories of things that have to happen. They're always a pair. If you have one, you always have to have the other. Oxidation. To be oxidized is to lose electrons. So whatever the thing that got oxidized is always going to be the element that experiences a loss. I knew I was going to do that. Loss of electrons. And what we're going to see once you learn how to do these, you're going to see that there is an increase in its oxidation number. Because we're representing the electrons, and the electrons have negative charges, so if you have less negative things, you get a bigger number. The thing that gets reduced is going to be the element that then gets those electrons, the element that experiences a gain of electrons. And so if you have more negative stuff, then your oxidation number goes down. Okay. So the first step is always going to be to assign oxidation numbers to every single element in a reaction, and then to see and try to recognize one of these things, like which one has gone up through the course of the reaction, which one has gone down through the course of the reaction. There's also something called an oxidizing and reducing agent, and it's so annoying, and I'm so sorry to like try to keep these two straight, but like the reducing agent is the thing that helps something be reduced. So it is going to be a reactant species. And I'll clarify that later, but like, yeah, we'll practice. That allows another species to get reduced. So the thing that gets reduced has gained electrons. The reducing agent allows that to happen. It facilitates something being reduced, which means that the reducing agent loses electrons. Woo! Isn't that so fun? It's a lot of like 3D chess in your brain to keep them straight, at least for me. So, you know, I get it if it's confusing. The oxidizing agent, therefore, is the reactant species. That allows something else to get oxidized. Definitely meant to write species up here, my bad. And species is just like a vague word we say to like refer to like any chemical. Like it could be an element, it could be an ion, it could be something, you know, like species. So it helps something lose electrons by being the one who gains electrons. I hate it too. It's fine. Okay. So like looking here, so I'll show you in a sec how to assign oxidation numbers, but that's what are up here, representing like how many electrons each atom kind of has relatively. You assign each of those, and then you look for a change. So on the left side of the arrow, magnesium's was 0, and then on the right side of the arrow, it becomes +2. So 0 to +2, it has lost electrons, therefore magnesium, that element, is being oxidized. Oxygen on this side has a 0, and then it ends up having a -2. So oxygen, the element, is being reduced. Okay? So I think that's the easier part to recognize, or like what I would always start with personally, is which one is getting oxidized, which one's getting reduced, and those are always going to be an element. And then it's kind of your reactant species that is the agent. So notice here how like magnesium got oxidized, but that means it's the reducing agent. It helped oxygen get reduced. O2 is the oxidizing agent. So not just oxygen, the element, O2, because like that's the species that it is as a reactant. I'll show you another example, but yeah. Okay, oxidation numbers. Hopefully you've seen this before. There's just a bunch of rules, and unfortunately it is just memorization. Sorry. I was gonna star like these are the most important ones, and then I just ended up starring all of them. So you just kind of gotta know them, unfortunately. The way I've separated these, like your first step is like these. Okay, sorry. Let's just kind of go through them. Pure elements always have an oxidation number of 0. And reminder, pure elements, that includes diatomics. So like O2, always a 0. I2, always a 0. Or like just a metal, those would all be zeros if you see them just by themselves. Any ion will have an oxidation number equal to its charge. So if you see just like a straight up ion, like that as a product or reactant, then its oxidation number is its charge. And then this one you're going to use a lot to figure out your oxidation numbers, because you only have a few that you're expected to kind of know as reference. Like these are the only ones that we kind of know. But then we use this principle to figure out the rest of the elements. So yeah, I would say like oxygen and hydrogen are the ones I use the most probably, but at a certain point, so maybe start with those ones. That'll get you most of the way a lot of the time, but you should probably learn the others too. Sorry. Okay, let's try this. So the way I do this is if you have a compound, or just, I guess if you have a reaction, assign any of the oxidation numbers you can. So any of these, just assign them all. And then any blanks, those are probably going to be attached to, like they're going to be in a compound. So you're going to figure those ones out based on these rules. So based on what they're bound to, you'll figure out their oxidation number. I guess I'll try to mix it up and try to show you a few different ways. The way I do it, mostly just because I have small handwriting, and so like this is what makes sense to my brain, is that I tend to keep track of my oxidation numbers like on top of my elements. That's just how I do. Like I always put mine on top, and your oxidation number is always per element. So I'm going to put a -2 here because my rules say that oxygen always has a -2, except for this. You do need to know that exception. So by putting a -2 there, I'm implying that each oxygen has that -2. Okay. So, figure out something that works for you. If you want to do this off to the side, that probably would make more sense for most people. But I write small, so I like to just kind of make notes under here. It's gonna be a pretty similar like it's not the same thing as charges, but the way you figure out oxidation numbers is pretty similar. They're always gonna sum to 0 or sum to a charge if it's an ion. So each oxygen has a -2, and there are 2 oxygens, which means that carbon Okay, sorry. So let's just, like I said, we're going to use this to figure it out. Neutral compounds always sum to 0. So far from the oxygens, I have a -4, and I have to put something here to make it 0, which must be like +4, right? We all see that, hopefully. And there's only one carbon, so each carbon must have a +4. Hopefully that feels okay. So our oxidation numbers would be +4 on that carbon and -2 on each oxygen. One of our rules is that, oh yeah, you probably should pause and like try these if you would like, but I'm just gonna keep walking through this. My rules are I always know that hydrogen with non-metals is a +1. There are 6 of them, so I have +6. And I have to have 2x plus 6 has to equal 0. So that is -3 on each one. So again, if you want to like write it off to the side, do each element by itself, like that can work for you. If you want to show more work with it to help keep track of these guys, or if you can do it in your head, then you can do it in your head. But you know, I'm a write things out enjoyer because I always mess things up. Okay, I think people get a little bit tripped up when there are polyatomic ions. My strategy for this personally is that I kind of treat polyatomic ions like a unit. So I'm going to pull out my polyatomic ion and just consider it by itself first. And I know that that has a charge of -1. So just looking at that first, I know that oxygens are always -2. And I have 3 of them, so I have -6. It has to equal -1 overall. So that means that my nitrogen must be a +5. So I think figuring out nitrogen is the hardest part here. Or, you know, if you memorize all the rules, you know that sodium is probably +1. But anyway, just want to show you that strategy because it will come in handy for more complicated ones where you don't have a group 1. Okay, so we've figured out all of these guys. So my oxidation numbers are here are +5, -2. And then to figure out sodium's two options. Either you could do like each element by itself and then it sums to 0. So I'll show you that one first. Here, I'll write it off to the side. You could do, okay, I got -6 and I got +5 and it has to equal 0. So my sodium must be +1. That's one strategy. Or again, you can treat the polyatomic ions like a unit. So to figure out the thing that's bound to the polyatomic ion, maybe you recognize that overall this thing is -1 and it has to equal 0. So sodium must be +1. Either way, whichever works for you. But our final oxidation numbers on each element would be +1, +5, and -2. Okie dokie. Now we just got a polyatomic ion on its own, -2, which means -6, and it has to equal -2, which means that this must be +6. So yeah, if you want more help, like I can show you others, like let me know. We can walk through that more slowly, but that's just kind of how I do it, just with like my little notes underneath for myself and then writing my final numbers on top. Okay. Sorry, another correction. I put on here that halogens usually have a oxidation number of -1, but the rule that they actually like would want you to rely on is the fluorine one. So that's my bad. I should have given you an example with fluorine instead, because the halogens are not, that's not an always rule. So here, okay. I'm just going to change this to fluorine. Again, it would be the same thing with chlorine, but I don't think they'd give you that and expect you to know that. So that's my bad. Let's try this one. Okay, so try it on your own first. Can you identify the thing that's being oxidized, the thing that's being reduced, and then the oxidizing agent and oxidizing and reducing agent? So first thing first, always assign your oxidation numbers. Things that are alone always have an oxidation number of 0. Fluorine always has an oxidation number of -1. Things that are alone always have a oxidation number of 0. So then I have to figure out coppers based on the fact that there are 2 fluorines. Copper must have a +2. And same thing for zinc. Okay, so when you're identifying what has been oxidized, what has been reduced, you're going to want to look for which elements have had their oxidation numbers change from the left side of the reaction to the right side of the reaction. So let's focus in on that. You might notice, okay, zinc went from 0 to +2. See that change in oxidation number? 0 to +2. That has lost electrons. Therefore, we know that zinc is oxidized. Okay, let's look for any other changes here. We got copper, and copper went from having a +2 on this side of the reaction to having a 0 on the other side of the reaction. So copper gained electrons, which means that copper was reduced. Oh, I can't believe I didn't even give you your little mnemonic. Hold up. I'm so sorry. Keeping track of these is annoying, right? So, I'm sorry, I totally forgot to say it. One way that you can keep track of, there's multiple. The one I use is oil rig. Oxidation is loss, is losing electrons. Either way, reduction is gaining. Or if you prefer, some people like saying that Leo the lion says grr. Whichever you remember better. Same thing. So yeah, mnemonics for you. Totally meant to say that. So that can be a helpful reference to remember these guys. I always write out just oil rig like every time I do a redox problem because I will forget. Or, at this point. Okay, you should just do that if you have any trouble remembering it. Cool. Okay, so we have our oxidized and reduced species. What about our oxidizing agent and our reducing agent? So oxidizing agent, that's going to be the thing that helps with oxidation. So we look back over to our reactants and we look at which thing accepted electrons in order for zinc to be oxidized. So I look at my reactants and I consider which one gained electrons. So it's not going to be zinc because zinc was the thing that was oxidized, right? And it's not going to be fluorine because fluorine didn't change its oxidation number. So I think that's the trickiest part, at least for me, for identifying the agents. It's not just a reactant, it's not just an element, it's like whatever species is on the reactant side. So in this case, it would be the copper 2+ ion that was the oxidizing agent. It might be helpful, maybe you want to you could do a net ionic equation, or a complete ionic equation and break things up into ions. Maybe that would make it easier to see. But you want to focus in on the thing that has the actual species that is on the reactant side. So not the whole compound, because the compound didn't gain electrons. Copper specifically got reduced. Copper is the thing that gained. And not just the element copper, the ion copper gained electrons and became solid copper. Similarly, when I look for what reduced my copper, it's going to be specifically my solid zinc. Oh yeah, I guess sometimes we want to be super specific, like say like exactly what thing it was. So our ion in solution and our copper, or sorry, our zinc solid was our reducing agent. Yay. And like, don't freak out too much about the oxidizing reducing agent thing. Like, I haven't found many problems where this comes up, so it won't be a huge topic, but it could be something that gets mentioned. So I wanted to make sure we covered it. Topic I wanted to give a little intro to is the intro to titrations. So titrations are a lab technique we use. It's a quantitative strategy, meaning we're trying to like get a number for something. We're trying to determine like an exact quantitative value. And what we're going to use it for usually is to determine the concentration of an analyte, is what we're going to call it. So the setup always looks like this. You got a fancy piece of glassware with all these little notches on it, these little measurements on it, and that is called a burette. And it has little numbers on it, so you're able to measure how much of the stuff you've added based on where it was before and how much of it you've added by the time you're done with your titration. And you fill your burette with some substance that we call the titrant. So this is usually something of a known concentration. And a known volume, because we have those marks on our burette, and we would specifically use something that we're very sure about the concentration of. Therefore, we can be very sure about how many moles of titrants we are adding at a given time. And so you turn this little knobby thing, and you drip, drip, drip your titrant very slowly into your analyte, which is sitting in an Erlenmeyer flask. Oh god, I'm gonna butcher this. No, not even close. It definitely has like an N in there, or I did not foresee writing this out. I should have looked it up. I think that's close. These flask. These are good for this specific type of thing. They have this weird little shape, so easy to swirl them. Easy to make sure they don't, like, you don't spill any out the sides because it drops into the bottom part. Okay, our analyte. So usually this is something usually we know like how much we added to the flask, right? Usually a known volume. But often what our goal is here is that we don't know its concentration. So what you're really doing here is you are dripping in a titrant very slowly into your analyte. And what is going to happen is there's going to be some kind of chemical reaction between these. So there's going to be a known chemical with extra bumps between titrant and analyte. So basically you're just making a reaction proceed in a very, very controlled manner. You're adding one reactant to the other reactant very, very slowly, or at least in a very controlled way, so that we know exactly how much of each reactant you have, exactly how much of the reaction has happened. And your goal here really is to be able to figure out the point enough titrant has been added to react with all of the analyte. Okay, so figure out that I've added enough that I've reacted with all of my analyte. Therefore, I will know exactly how many moles of titrant I added, and from my balanced equation, I can figure out exactly how many moles of analyte reacted, and I can figure out its concentration from that. So a few different things we need for this to happen. There's usually an indicator. So I mentioned this with the pH thing, very similar. Some kind of chemical that can color change. And we will purposely choose one that changes color at the point where the reaction is done. So there's lots of different types of indicators, and you would have to choose one that would work best for your reaction. To change color when reaction is complete. Okay. Equivalence point. So this is our fancy word for the point at which all of the analyte has reacted with the titrant. So this is where we know that we've completed our goal. This is the point, and we really want to catch that exact point where it has been completed. That way we can really accurately determine that concentration. If you have a 1-to-1 reaction, 1-to-1 mole ratio, then this is the point where the moles of analyte are equal to the moles of titrant. Endpoint, pretty much the same thing, just technically this is when the indicator changes colors. You just might hear both words, so I wanted to clarify. So if you chose a good indicator and did your reaction carefully, this should be equal to your equivalence point. Equivalence point. Okay. Again, we have a whole unit about acid bases, and titrations are very much a part of acid bases, so we'll be doing a lot more with this. This is very much just an intro. It's just something they like to throw in as a common lab technique. So here's your intro. We'll spend way more time on it later. I don't want you to stress too much about it quite yet. But there's different types. The main one usually is acid-base titrations. This is going to be an example of a neutralization reaction. So you are going to be adding an acid to a base and causing them to react together, creating just water and salt. There are different types of reactions, or different types of titrations. We'll learn about those when we do our more in-depth unit. For now, I only want you to care about, like, if I had a strong acid and a strong base, what would happen? So let's kind of read, like, what the data we'd get out of this is always a titration curve, so let's kind of make sense of this. If it's an acid-base thing, then our y is always pH, so we're measuring our pH of our reaction. Our x-axis is going to be the volume of titrant added. And then if it gives you a title like this, titration of something, that is the analyte. So here, I'll just draw it out for you. In this situation, you have a strong base. And we are dripping it into our reaction flask, our Erlenmeyer. Wow, those are not going to work very well if they are off-center, something like that. And we are dripping it into an amount of strong acid. Okay, so that's like the setup. So down here, this x-axis is saying, like, okay, starting at 0, I'm just dripping it until eventually I add 25 mils of the titrant. So you can kind of think of, like, it's similar to like, this is the beginning of the reaction. When you start the experiment, this would be the end of the experiment. So let's kind of label the parts of the curve. It always looks something like this. If it's a one, if you're only taking off one proton, it always looks like this. We got a flat part at the beginning, so that's the start of our titration. And we are measuring the pH in this flask. So we're talking about in the flask, in the reaction, what is happening here. This first flat part, and it with our setup, before I'm like, oh God, sorry. At the beginning of this, I haven't added very much base yet. So in my flask, there's more acid. Whatever your starting material is. And then at a certain point, you see this big ol' shoot up in your curve. And there's a point in the middle of that, I don't remember what it's called when there's like a straight up and down in a curve, but in the middle of that, that is your equivalence point. And if it's a 1-to-1 ratio, that means that and we're doing an acid-base one, that means that our moles of acid are equal to our moles of base. If they're both strong acids, this point is always going to be pH 7. And you can see that that is the case. Okay, and then if I kept adding more and more and more of my base, of my titrant, then we would end up with this, we would get another flat part. So this would be end of titration. Or not, I don't want to confuse you with thinking it's the end point. This is, let's say, like after equivalence. Now we're just dripping more and more and more base. There is an excess. Or whatever your titrant is. Okay, so that's the basic setup. That's all I wanted to cover for this. We'll talk more about this and see some examples in class. Hope you have a wonderful weekend, etc. Bye.